In our Open HPI's confidential communication in the internet, now we want to consider some traditional encryption methods to get a feeling what encryption means and how does it work. And these traditional encryption methods are methods that are far before the computer and internet time. So these were symmetric encryption methods, because the asymmetric ones were detected 30, 40 years ago. Let's start with the substitution ciphers. This is a group from ciphers, and in the substitution ciphers, each letter, each character of a text, of a plain text, is replaced by a different letter. Each letter by a different letter of the same alphabet, and the alphabet we are using is a Latin alphabet with 26 letters. And a special case of the substitution cipher is the so-called shift cipher, and also there are several shift ciphers. And the idea of this shift cipher is that the ciphertext is generated by shifting the letters of the plain text by n positions in the alphabet. Each letter is shifted. It's shifted by the same number of positions. One of these shift ciphers, historically very famous, is the Caesar cipher. And Caesar, yes, the Roman Caesar, here he used this shift cipher for encrypting messages about wars and other things by shifting each character by 3 positions. So, for example, from the word hello, the German, say the English word hello, we get the key door word. So it's no connection, but you see here we have on the 3rd and 4th position the same letter. When we shift it by the same amount of positions, of course, we also got same. What is the key in such a shift cipher? The key, clearly, that's the n. That's the number of positions that are used to move the letters to produce the ciphertext. And the n in a Latin alphabet can between 1 and 26, so the number of keys is 26. So this is a very low number, and this low number, of course, allows brute force attacks. Why? Brute force says, try out all keys up to the moment you find the right one. And when realized to have the right one, if the useless, the stupid text changed into a meaningful text. When we have only 26 different keys, we can start with n equal 1, with n equal 2, with n equal 3, and after a short while, we have tried out all the different possible keys, and then we can decrypt the ciphertext. There are other successful attacks possible for such simple shift ciphers, and one is a frequency analysis. And the frequency analysis is based on the appearance of the different letters in a plain text. And what we see, each language is characterized that in the text of this language, the frequency of one letter is about the same over many such texts. So, for example, the letter E comes in English text is in English text most frequently, and comes with an occurrence of 11%. The letter A is 8%, the letter R is 7%. And now we can analyze the ciphertext and can check the occurrence of the simple letters, and then we can try out according to this frequency of the different letters to change into the right ones. Because we have only one text, we have a little bit to play with it, because in a single text this distribution can be differ from all the texts, but it is a simple approach for cyber attacks. Another substitution cipher are so-called permutation ciphers. And the permutation ciphers is that we have a table. We have a table with the alphabet, and then below of each letter there is another letter of the alphabet. So we can mix it as we like. Important is that we have our 26 characters, that we have 26 other characters. So A, B, C, can R, S, L. And then we generate the cyber text, by from the plain text by replacing accordingly to this table the different letters by the other letters. So a permutation is a function which assigns each letter of the alphabet another letter in the alphabet. It needs to be an isomorphic function. That means all letters have an origin letter. So the letter Z is assigned to P of Z, and P is a permutation over all the letters of the alphabet. So here the key is a permutation, is the assignment of the different letters, and the number of assignments. This is really big. It is 26. This is the number of letters, the size of our alphabet. And this is faculty, because we can have all the sequences, can use all the sequences. And we know 26 faculty is more than 400 quadrillion. So here now we have a huge space of keys, and a brute force attack to try out all assignments, all permutations, needs really a very long time. The 4 quadrillion is 4 times 10 to 26. Even more difficult than this permutation ciphers, which is a substitution cipher, are ciphers from the polyalphabetic ciphers. And the idea here is that we can use different letters for a replacement of one letter in our plain text. So here we can make the frequency analysis, which is applicable to the permutation cipher, but it is no more applicable here, because we can replace a letter E, for example, by many other letters. So sorry, here is a mistake. So it's 11 different characters, because the E has 11% of the different character. So frequently occurrence letters are encoded by different characters, so that it's more difficult or impossible to apply this frequency methods. But also here, against this polyalphabetic ciphers, one can design attacks based on the statistical analysis of the frequent letter combinations. One is no more looking to the single letter. One considers different one positions of 2 or positions sequences of 3 letters, and investigates the occurrence of such 2 or 3 letter tails. To make it understandable, to give an example for such a polyalphabetic cipher, look please to the Wegener cipher. And here the idea is, by constantly repeating an agreed keyword, a key text is generated in the length of this plain text. So we take a keyword, and then we repeat and repeat and repeat this keyword as long as the length of our plain text. And then the cybertext is obtained by adding the plain text and the key text, letter by letter. Adding means the position of the position of the letter in the plain text is changed, is shifted by the position of the corresponding letter of the key text. To make it more clear, we have our plain text. Plain text is short, is an example, state secret. And our keyword is secret key. Now we repeat secret key as often as we have the length of the secret key. And then we can add this two letters. That means we shift the letter S by the position of S in the alphabet. And then we shift the letter T by the position of the letter E in the keyword. And then we shift A by the position of C. And in this way we get this part, and this is quite interesting encryption methods. It's simple to perform, but difficult to attack. With this, there are different famous examples of this polyalphabetic cipher. One which is very interesting from a theoretical point of view is so-called one-time pad. And the one-time pad is a special case of the Vigenère cipher. And here the choice of the keyword. The keyword is not generated by repeating a short keyword as long as the length of the plain text. Here the key is generated as a randomly sequence of letters of unlimited length, so that each plain text we have such a random sequence of letters as a key for this computation. If we apply this method to a binary alphabet, not to our Latin alphabet, to our binary alphabet, and this is the situation we have in the computer world, which we have in the digital application, then we can prove the following mathematical theorem, which says the one-time pads, which are operated by true random sequence, have perfect secrecy. There's a perfect security. This is mathematically defined, what it means. So by having a real true random sequence of 0 and 1s, and have our message of 0 and 1s, then we get with this one-time pad a very secure encryption method. The advantage of this very secure method is that it's very simple procedure. Very simple procedure that can be used by each layman with paper and pencil. So agents always carry out a sealed envelope with a longer random sequence they got from their agency, and then if they have a message, they take this random sequence and they encode the plain text. Problem here is to get a real random sequence, because it is not so easy to produce such a very long random sequence. There are pseudo-random generators, but here for this validity of this text of this mathematical theorem, it's very important that it's a real random sequence. And this makes it difficult for exchanging the key, because both partners, it's a symmetric cryptographic method, so both communication partners need that key, need that random sequence. By the way, there are ideas to use signals from a satellite which can be received on any place on the Earth, and then if they both synchronize their watches, then they can get such a random sequence. So there are many methods. We have not the time to go into detail, but it is difficult in the sense that transmitter and receiver must store such very long keys and have to deal with such very long keys. Perhaps the last example are rotor ciphers and the Enigma encryption machine. Here are some historical facts about this Enigma, which is the famous example of a rotor cipher. As late as the First World War, radio messages were encrypted with a further developed Vigenère cipher. So this Vigenère cipher has many applications and were very popular in the use of such encrypted, mostly in military applications, encrypted things. So around 1980, a rotor cipher became independent, invented by at least 4 different inventors, and a rotor cipher works as follows. One has different such rotors which can be moved, and on each entrance there is one letter, and so and this inside the rotor there are different. This is in permutation cipher, so there are different connections for the single letters. So for example, when we start to put C into the first rotor, we get a B. And then the B is moved by the first rotor to an A. And then the A is changed into a D. So if we use more of such rotors, we can generate very different and very difficult encryptions, difficult for cryptoanalytics. So the most famous representative of the rotor ciphers was this Enigma machine, this Enigma encryption machine that was used by the German army in the Second World War. Not only the army, but also the marine used it. And the people felt that it's unbreakable. But a very famous mathematician, Alan Turing, he got a lot of support from the English army, so they established a fabric with thousands of people that worked on the decryption of this Enigma machine. And at the end, even before the Second World War was finished, they were able to read the encrypted German messages. And of course, this brought a big advantage in the fight between these two armies. We will have an excursus on rotor ciphers and the Enigma. Who is interested in more details, we have it in our course. I think this gives some examples about the idea of encryption, how it worked. And the traditional examples, of course, are very easy to understand and simple to apply. So it helps us to get an understanding of this, at least of this symmetric encryption methods.